Hello and welcome to our presentation. We did our project on distributed data structures and we built a library for that. I'm David Krakauer.
I'm Colin Rioux.
I'm Yujie.
I'm Tianyi Liu.
So first, to start on our problem, we saw that there was a bunch of complexity within distributed systems, specifically, transitioning data structures from traditional data structures, things like trees, queues, hash maps, all these things, transitioning from a traditional sort of static allocation to a distributed environment is kind of one of the more complex problems that comes up. So individually, we kind of split up and researched individual data structures for all those different ones. And our goal was to build a library that had a bunch of different data structures. That way we could each sort of take one of those data structures and really hone in and focus on it. So we found a bunch of research, we implemented a bunch of different solutions for those data structures under kind of one generic hood. But overall, our general problem was to streamline the organization of common structures through a library of distributed data structures, ultimately to allow developers to spend their time where it matters in sort of that system architecture and that system design area rather than getting stuck on the nitty-gritty data structure part.
So in our distributed data structure system, data are stored across different nodes, and in each node, it has its own process and a memory space, which can be either on the same or different machines. Nodes are communicating with the main process via networking ports, which mean every object needs to be serialized into a stream to be sent via ports. Also, data are stored in the memory of each node process for fast retrieval, but it's also ephemeral. Next slide, please. Next slide, please. We are currently have 4 data structures implemented, which are distributed hash table, distributed queue, distributed tree, and distributed linked list. Next.
Yeah, so this is our distributed system. As you can see on the picture on the right, we have 3 groups. In the case of our code, it actually can scale to as many groups as we want. And the idea is that each group has a leader node and 2 clones of that leader. So for the replication fault tolerant problem. And the client only sees the 3 or X amount of leaders. This is to just, keep things pretty straightforward and minimal. So the client doesn't need to store a huge table of 9 nodes. Instead, they're storing 3. And theoretically, like each group could connect to another group too. And then clones do know each other. So in group 0, you can see that there's 2 clones. They do know that there's 2 clones. So there's another one that exists. And this is really only there so that they can do an election process on leader failure. As for management, so for fault tolerance and availability, we implemented a heartbeat system. So the leader will send a heartbeat like every 50 milliseconds to each clone. And then if the clone doesn't receive a heartbeat in a certain amount of time, I think it's like 100 millisecond threshold, just to account for delay, they'll perform the leader election algorithm, bully. And then as for performance, we're doing multi-threaded for the socket message handling on the workers. So on the leaders and the clones. And we're also doing smart data storage and access for the data structure. So we're definitely doing mutual exclusion, and we'll talk about that in a second. And then for scalability, we are grouping the workers, as you saw in the previous slide. And the client only needs to know the leaders, right? So we could have 100 groups, right? And if it's 3 workers per group, then you have 300 workers, but the client only needs to know about 100, which is a significantly smaller memory footprint. And then for consistency and concurrency, we do have mutual exclusion. And then we also assign a unique ID to the data structure and its data. So if you create, for example, two queues, right, and then try to store their appropriate data on the nodes, you can be able to distinguish them which data that queue belongs to. So just to kind of briefly talk about the hash table, which I implemented. This is not to be confused with a distributed hash table, which is what's used for peer-to-peer systems and stuff like that. This is just a standard hash table in a distributed system. So we have the client, and they hash the data, the key, and mod the key or mod the key with the group, and that they find that they're able to find the worker from that, or from the group that's storing the data. And then on the workers themselves, so on the leader, for example, there is a non-distributed hash table, right? So then we get fast read and write access, 0 of 1 lookup, stuff like that. And then as for the worker, it hashes the table name and hashes the key and adds them together to get the location for the table entry in hash. So that's how it's pretty nice and quick. And then we support 4 methods for hash tables, which is has, get, remove, and size.
Our queue basically have 5 functions available. First is in queue, which stores queue items evenly across nodes as shown on the graph. And also there is dequeue, which removes an item from the queue in a first in, first out order because it's a queue. And also there's display, which prints all items from the queue. And there's a get size, which returns the size of the current queue. This data is stored locally in the main process, and it's updated every time a in queue or a dequeue is called. Lastly, there's a destroy function which deletes everything. So on this graph, there are 2 pointers. Every time a in queue is called, the real pointer will move. For example, if we in queue entry 8, the real pointer will point to node 2, indicating it's the new tail of the queue. And also for the head pointer, every time a dequeue is called, for example, entry 0 is deleted, entry 3 and 6 will come forward to fill in the gap. In the meantime, the head pointer will go to node 1 and pointing to entry 1, indicating it's the new head of the queue. So both of the pointers are going to iterate through every node.
Awesome. That moves us on to tree, which was the data structure that I implemented. It represents a sort of modified binary search tree, which I'll discuss what modified means in the next slide. It supports kind of the traditional tree methods such as insert, search, remove, and traverse. And if we can go to the next slide, I can talk about what exactly I mean by modified BST. So when you're talking about a tree in a distributed system, there's kind of 2 general ways you could implement it specifically with our generic system. So the first way is to just have each group hold its own BST and have that sort of align with strict BST rules. So then when you're looking to do a traversal of the whole tree, you can grab the sub BST from each group. You can combine that into a modified BST where you just point the root of each of them to the same node, which kind of breaks the traditional binary search tree rules. But then you get just a traditional tree, and then you can return the traversal of that tree. Or alternatively, you can grab the first binary search tree, and you can grab the nodes from the other search subtrees, and then you kind of compile a list of nodes, which you can then from there compile into a kind of a true BST by reinserting all those additional nodes, which then you can return. So for our project, just for simplicity's sake, we implemented the first one, but ultimately, you would have to choose this based on the application of the tree, which one would be more useful, whether or not you care about the strictness of the binary nature of your tree.
Okay, so for my data structure is linked list. So it's kind of work like a queue. So we're gonna save the node across different node. So for example, the head will go to the node zeros, and then the first one will go to the node 1, and then the third node will go to the node 2, and then we're gonna go back to node 0. So we're gonna keep like just like the picture here. So it only like supports 3 methods: the insert, delete, and find.
So that brings us to the demo. So I'm going to stop sharing real quick. And all right, so we're going to go ahead and compile our code here. We're going to cd into source. We're going to compile our files, and then we are going to run dsystem here. And dsystem, just to clarify, that is the name of our client program. And what it's doing right now is it's initializing the distributed system. So it's creating, in our case, 3 groups. And we're going to go back up to the top here, and it's creating 2 clones per group. So just to clarify, we have 3 groups. Each group has 1 leader and 2 clones. So that is a total of 9 nodes. Now you can see in this screen share here that we are simulating both the hash table, the queue, tree, and a linked list. So like for the hash table, right, we just create an empty hash table, then we insert X and Y, and then we actually remove Y, and we check if it's actually removed. Similar kind of situation for the queue, right? We are basically, it's not shown here, but we're enqueuing 0 through 10. Then we pop off 0, and as you can see, it prints in order. Tree, we are inserting 3, 6, and then 9, and then printing if it's reversal, and then it's kind of similar behavior here for the linked list. And if we actually pull up one of our worker logs, so in this case, you can see I'm opening 7001 here, which is actually just our leader on group 0. You can see that it's booted as online, and we're receiving some messages. So we're receiving, okay, hey, we're cloning 7002, 7003. They're knowing their neighbors. And then we're sending all different kinds of messages back and forth to do all the different behaviors for our tree structure. In addition to that, we are also, let's see here. Yeah, sorry, I missed it. We are sending heartbeats every so often. So here's an example of a heartbeat that was sent. And if we actually look at the clones, they're receiving forwarded packets for data replication, and they should have also received a heartbeat at some point. But yeah, right here. So I received a heartbeat. So I'm going to go back to the slides now.
So for the major challenges, we have like 3 major challenges. The first one is deal with the multi-threading. Since like just like previous state, we have like more than 1 thread. So we need to deal with the in-order reads and the writes on all the workers. The second challenge we encounter is how do we store the tree and the linked list. So for both tree and the linked list, it stay as like a node. So we have to find a way to like save like different nodes into different groups, and then we also need to figure a way to reconstruct it if user required. And then the last challenge we encounter is debug worker node process. So it's kind of similar like the first challenge. So since like we have multi process, so more than 1 workers, so it will encounter like more problems to figure out like what's wrong with it, and then where's the bug come from. So this is why like we have like a debug inside our client in our like client process in the client programs to then this way we can clearly to see the like is message being sent, is message being received. Next slide, please. And then for the next steps, so right now everything is working work on 1 computers. So everything is saved in, so it's kind of like simulations. So in the futures, we want to make sure it like work on like more than 1 computers, to work across different computers, and then different computers will communicate with each other via like a remote procedure calls. And then the second, we definitely want to support more data structures. So right now we only have 4. We wish to support more like stacks, graph, and heap. And then for the last ones, we definitely want to increasing the abstractions. So right now it is kind of like fundamental. It's still like simulations. We definitely want to create like a user interface to make it easier for user to save their data.
Thank you.